Next, it's my pleasure to introduce David Graham, who's the co-founder and chief science officer of Aspinity. He's also professor of computer science at West Virginia University. His research focuses on low-power electronics, analog mixed-signal ICs, and neuromorphic systems. He has lots of awards, and he received his PhD in electrical and computer engineering from Georgia Tech. So, David.
Thank you. My name is David Graham, and today I'm going to talk to you about AnalogML. AnalogML is the idea that we can shift some of the machine learning workload from the digital domain to the more efficient analog domain. This allows us to do inferencing right at the sensor interface before we even digitize the signal. So as a result, we can actually build extremely low power, always-on sensing applications. So we're going to start out by going through why we want to look to analog processing for significant power consumption wins. It is particularly important for battery-powered applications that are always on and always sensing. Then we'll go through a quick overview of our AnalogML technology and see how we can do machine learning completely in the analog domain. And lastly, we'll get to a couple of different audio applications just to demonstrate the operation and performance of these types of systems. So I think we're all very well aware of the explosive growth of wirelessly connected sensing devices. And all of these sensors are generating just huge volumes of data that we then have to process to make sense of or store for later processing. But either way, there's real need to be able to process all of this information as efficiently as possible. But not all this information is useful. In a lot of applications, most of the information coming into these systems is just irrelevant noise. And we're wasting lots of power and compute cycles processing all of it. So for example, take a voice control system. A voice control system has to be always on and always listening so that it doesn't miss a wake word, which could happen at any time. But you're never going to actually hear that wake word unless somebody's talking. And in a typical home environment, most of the time it's just ambient noise where nobody's actually speaking. So we're wasting all of this power processing noise where you're not going to actually even ever find that wake word. And so all this extra processing is particularly bad for battery-powered devices because it just drains the battery. So it's really critical that we come up with ways to determine the relevance of the information as soon as we can so that we can then spend our resources processing the relevant information. So let's take a look at where a typical ML system can be inefficient and may be wasting some power. So the physical world is analog, and all signals that come from the outside world are analog signals. In a conventional always-on system, we'll take those analog signals and indiscriminately convert all of them into the digital domain as soon as we can so that we can do all of our processing digitally. There's no guarantee that any of that information is actually relevant, and you won't know until after you actually digitize it. And just that sheer process of digitizing the signal through an ADC can be relatively power consuming, not to mention the whole digital processor itself. So as a result, it can be really hard to build systems that can last for a very long time on a battery or a single battery charge. So even getting to a month can be a real challenge on these types of systems. On the other hand, if we were able to do some of the processing in the analog domain of that raw analog signal, we can determine the system relevance right away. We can leave the rest of the signal chain in a low power sleep state until we actually need it. And when the AnalogML system is able to determine the relevance, you can wake up the rest of the part of the system to do further processing, if you even need to. So as a result, you can build systems that are extremely low power. And we're looking at building systems that are less than 100 microamps of current draw. So suddenly, we're talking about systems that can last for multiple years on a single battery charge. So the rest of this talk is going to be about how we can build these analog ML systems that allow us to get this system level of energy efficiency and allow us to build things that can last for a very long time on a battery. And we're going to start out by looking at the efficiency of analog. So I think it's well understood, and we've known for a long time that if you want to do high-resolution processing with many bits of precision, digital is clearly the way to go. But it turns out the converse is also true. If you don't absolutely need to be working at the highest levels of resolution, analog versions of compute functions can be much, much more efficient than their digital counterparts. This is true both in terms of the power consumption as well as the area on a chip to do these functions. And it's interestingly, we're seeing some trends, particularly here in the tinyML space, where a lot of machine learning algorithms can be robust to some of these lower resolution processing. Now, the exact location of the crossover point between where it becomes more efficient to do processing in either the analog domain or the digital domain depends on the specific operation that you're trying to do. And one really interesting example to look at is the multiply accumulate function, which is so critical for neural network applications. In a digital implementation, it takes many, many transistors to do it, but in analog, you can do it in just a few transistors and at dramatically lower power levels. And for this reason, we're seeing lots of interest in doing that function, that very specific function in the analog domain. So we're seeing a lot of analog compute and memory techniques that will convert back to the analog domain just to perform the MAC function because it's just so efficient. But you can do a whole lot more than the MAC function in analog efficiently. You can build entire signal chains that are extremely low power. So the big question is, why aren't more people doing this? The reason, I think, is that working with analog systems is pretty challenging. Digital systems, on the other hand, are really easy to use. You can write some code and easily spit out a solution. Digital systems are broadly applicable, and you can have a lot of versatility and apply it in many different applications. And additionally, with digital systems, you can get a lot of repeatability. It's easy to get the same result from chip to chip. All these things can be really a big challenge with analog systems in the traditional sense. So we're going to spend the next few slides talking about our AnalogML core and talking specifically how we address these issues with analog so that it makes it easy to work with analog systems and get really good results out of them. So AnalogML takes inspiration from analog signal processing, machine learning, and reconfigurable computing. Everything on this analog technique is software controlled. And so we can use software to define and control analog circuits to perform functions like sensor interfacing, feature extraction to pull out the salient information from signals, classification and event detection with a neural net, and even analog data compression of incoming signals so that we can store a history of that signal for later use if needed. Our AnalogML core consists of a wide variety of different analog blocks that are configured in an array. And software controls everything, and software controls the configuration. The configuration in the sense of how individual components are connected together in terms of the signal flow, as well as the different parameters of those circuits to help control the function of those analog circuits. The AnalogML array is subdivided into computational analog blocks. And those computational analog blocks have different analog signal processing elements, as well as analog non-volatile memory. So the analog non-volatile memory, it's embedded in each of those signal processing elements. It's based on a custom and proprietary floating gate-based technology where we can store analog values instead of digital ones and zeros. And we use this analog memory to control the parameters of the circuits, but we also use it, almost even more importantly, to deal with things that typically limit the application of analog to lots of, that limit the applications of analog to getting really precise and repeatable results. So things like, like offsets, mismatch between devices, other PVT types of concerns as well. So we can mitigate all these effects. So not all CAB elements are the same. Up towards the top where the sensor information would come in, we have CABs that are specifically tailored to being able to do things like sensor interfacing. And as you progress farther in, you'll see things that, cab elements that are very capable of doing analog pre-processing and creating a whole variety of types of features that you can then feed into a multi-layer neural net. And for good measure, we've got some mixed signal and logic capabilities that can help control timings and some extra decision-making tasks. Not all cabs need to be used. Signals can be routed from any one cab to any other cab. And if you're not using a cab, you can just turn it off and it doesn't consume any extra power. And so because we have so many different types of things here, we can really begin to think about building lots of different types of applications. So let's dig in a little bit to the analog neural net and see how we can implement a neural net in the analog domain. Conceptually, it should look and feel exactly the same as any other neural net. It's just that the underlying computations are done in the analog domain. So for instance, we use a custom 4-quadrant analog multiplier to multiply the inputs by the weights. And the weights are stored they're stored as analog non-volatile memory elements that are embedded right in the multipliers themselves. So there's no need to go fetch weights from memory or anything like that. And the outputs of the multipliers are currents that you can then sum onto a single wire, and then you can feed that result into one of various different types of activation functions. So our current chip has 3 dedicated matrix multiplication blocks that can be configured to do fully connected and recurrent neural nets. You can also segment these blocks via software to define the appropriate numbers of layers and the sizes of those layers. And it may be a relatively small neural net, but we found that it's surprisingly capable of doing a lot of sophisticated classification tasks. And a large reason for that is much of the heavy lifting is done by the feature engineering, getting good features that feed into the system. And we have a lot of capabilities because we can really define what we want with all those different cab elements. Working with these analog neural nets should look, again, and feel very much like any other neural net. In fact, we train with standard tools like PyTorch. And once we're done with creating a model, our SDK is able to just take that resulting model and map it to weights and connections on the chip. So we have all these blocks. We've got a neural network. Let's see how we can kind of put these all together to make just a really simple, generic analog signal processing chain, audio signal processing chain. So we have an SDK that has a library of components, and each of these components map back to elements in the cabs or combinations of elements in the cabs. So that you can just instance those components. And then we also have a language that allows us to string these components together to make an entire signal chain. So for instance, in this case, you might want to start with some sensor conditioning of the incoming sensor, so like getting rid of the DC offset, filtering high frequency noise, appropriate amplification. And then you can feed it into, if you need it, some analog pre-processing blocks before you split it up into features. And a really simple example of a feature you can do in the audio domain would be some form of a spectral decomposition. One way you could do that is to instance an array of filters and then take the outputs of those filters and feed them into envelope detectors to understand what's happening in terms of the magnitude in each of those subbands. Lastly, you can feed those into the classifier, and then the SDK will be able to compile all of these connections and everything into a bit stream that you can then load onto the chip. Because everything is software controllable, it's really, really quite easy to work with these analog systems without even thinking about the fact that they're actually analog, and quickly build and develop new applications. So we recently announced our first product based upon this AnalogML concept, and it's the AML100 chip. And we've already built lots of applications on various different types of sensing modalities. Let's take a look at a couple of different audio applications, real-world audio applications. Glass break detection is a really good use case for this. The glass break event is very short-lived. You never know when it's going to happen. and it's a lot of noise and junk data in between. But it has to be always on. So you can train the AML100 on a variety of different features, like spectral energy, SNR estimates, zero crossing rates. All these things are available in the SDK as different library components. And in order to improve the classification accuracy and prevent false triggers, just to give a little bit of an understanding of how you can work with these systems, you can classify based upon different portions of the sound of the glass break event. So for instance, the onset of a window break has a thud of something hitting it, and then the latter parts of the sound will have the more typical shattering sound. And so you can train for each of those parts as different classes, and then use some of that mixed signal and logic capabilities that we talked about to ensure that the right sequence of events happens. And so you can build all this, and it consumes only 60 microamps of current to do all this in the analog domain. Most of that's actually coming from the microphone itself. So you can, with these power numbers, you can realistically think about building systems that can last for over 4 years on something as simple as a couple of AA batteries. Another application that's a good use case is voice processing. And this one, specifically, we're looking at how you can use the AML100 to wake up a higher power classifier. So for instance, you're never going to hear that all-important wake word unless somebody's talking. So we can train the AML100 to look for human speech. And only when it hears voice activity does it wake up the higher power wake word engine to do its thing. And you want to make sure that the voice activity detector is very discriminating, because every single false trigger or false positive is going to wake up the system and needlessly drain the battery. So for instance, you don't want to use something like a simple acoustic activity detector that's not as discriminating, because it'll just wake up the system far too often. So we're able to train our AML100 really to key in on the signatures that recognize human speech and do it with really good accuracy. And it only consumes about 10 to 12 microamps of current to do that. But another important consideration is that you provide enough information to the wake word engine to be able to make a correct decision. So many of the big wake word engines out there require a certain history of the signal, of the sound, prior to the start of the speech. They need that in order to make sure that the noise suppression algorithm has enough information to be able to correctly work. If you don't have that pre-roll of information or that history of information, then the wake word engine will take a big hit in terms of its accuracy. So what we can do is we can actually have the AML100 continuously bring in and understand or monitor that incoming sound and compress that audio signal into a lower bandwidth signal that we can then send to a circular buffer to maintain a history of that signal. And then once the voice activity detector wakes up the rest of the system, you can decompress that pre-roll of information at faster than real time, stitch it to the front of the live audio, and now you have all the information that you need for the wake word engine to be able to maintain good accuracy. And additionally, it doesn't have any hits in terms of the latency of detection. So being able to do this, we're able to implement all of the voice activity detection and the pre-roll compression on the analog chip. It only consumes 15 microamps of current. And if you think about the entire system, in always listening mode, it consumes less than 100 microamps of current. So to think about this in another way, or to put it in another way, this type of cascaded wake up with pre-roll allows you to work with a higher power processor or digital processor that wouldn't be able to necessarily meet the power budget on its own. So for instance, if you have a high power, or you've got a classifier that you've developed and it requires being operated on a higher power processor, or you just have this embedded platform that you really like to work with, this cascaded wake up allows you to keep the system level power consumption down. And it maintains an average power consumption that's very low. It's typically an order of magnitude or less than the power consumption of the digital processor of its own. This allows you to start thinking about building a whole variety of new types of applications that weren't previously possible. So just to summarize, we've talked about AnalogML, which allows you to do machine learning in the analog domain before you actually digitize the signal. Everything is software configurable on our chip, on our AML100, so it makes it really easy to develop new applications. And we've got a lot of different capabilities on it, so you can apply it to many, many, many different applications. Additionally, things like our AnalogMLTM allow you to mitigate so many of the effects that typically plague analog circuits. And suddenly we're able to start being able to have systems that are repeatable across many, many chips. So in summary, analog is efficient. The AML100 is what allows us to access all that efficiency and build really, really low power systems. So thank you for listening, and please let me know if you have any questions.
Yes, we have some questions. Go ahead.
Thank you for your talk. It's very fascinating. So I'm wondering if you convert your analog signal into digital in between your front-end feature extractor and your neural net, and if not, how do you deal with the signal-to-noise ratio degradation and signal distortion issues when you concatenate analog blocks?
So no, we generally keep everything in the analog domain. We don't ever convert to digital until after we make a conversion on, or a decision on what was happening. So basically the features here are in that reconfigurable framework that we have, and then we pass that to a neural net, and everything there is analog. So in terms of the signal-to-noise ratio, we don't, so because we have the ability to create a whole variety of different types of features, our signal chains never have to get to be too terribly long. So we don't get this huge accumulation of offsets or noise from one stage to the next. That's really one of the big benefits of this, is that we keep the effective signal chain of the analog circuit pretty short so that you can get a good result out of it.
All right, thank you.
Yeah.
So microphone is kind of draining most of the power. It's most dominant component there, right? And I'm just curious, like, have you benchmarked a digital processor with 4 bits in comparison with analog? Because even if it's like 2 times or 4 times slower or drain more power, it's still, in comparison with microphone, looks reasonable then. Like.
So I think the question was, have we benchmarked it against really low resolution digital processors?
Yes, yes.
Yeah. So, one of the biggest problems is that you still have to convert it to the digital domain, and that ADC process is sort of a limitation on how low you can go in terms of the power consumption of the entire system. So we're not really thinking about, we're more thinking about not just the power consumption of one individual component, but what is the effect on the entire system itself. And so you really can't neglect the entire signal chain in that case.
Thank you for the great talk. My question is on the multiplier that you mentioned. So that uses NVM technology to store the weights. Can you comment on what material you're using? Is it PCM or is it other,
Oh yeah, so the AnalogMLTM. So the AnalogMLTM is it's our own custom floating gate-based technology. It's completely compatible with any standard CMOS process. There's no extra add-ons that you need to do. You can put this in any, basically a vanilla CMOS process.
I see. And what about the activation functions? Are they also in the analog domain?
Yes, yes. All in the analog domain. So again, we got this multiplier. They all come in. We feed them into, basically the output's a current. And then we take that current and feed that through another circuit that we can configure to do sigmoids, ReLUs, tanh functions. And then that's the output of the neuron itself.
Okay, thank you.
Yeah.
Last question, please.
This works for a hot wording, but typically hot wording, right? Hot word.
Oh, okay,
Okay.
yes.
But typically on cell phones now, you have noise suppression, you have hot wording, music examination, glass break or dog barks, ultrasonic, and perhaps environmental car door slamming, train, airplane. So how does this work if we have everything that typical cell phones now examine?
I think that means what happens when you have lots of different kinds of noise and interference, very complex audio coming into this classifier.
Yeah. Yeah, so it all comes down to the training, and really it's those features that you go into. We really spend a lot of time doing the feature engineering to be able to discriminate those sounds. So all these other interferers have different types of components and information than, say, the human speech. And this is just one example of things that we can do with it. So are we classifying all those things? So at this current point in time, no, we're looking for a specific subset of those things. In a future could potentially go that way to get more types of classifications. But right now we're kind of looking at it from a, this is a specific task that we're looking for. And really kind of getting the relevant information. So all that would be kind of noise in a particular application.
Great. Thank you very much.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymex, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, Pixart, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.